Hello, welcome. In this video, I'm going to be deriving the equation for mean drift velocity of charges that flow around a circuit. So the equation I equals nAve is sort of beginning with the end in mind, what we want to get to. But we will begin with just a general definition of current. And so current I, the intensity of the current, if you're wondering why we use letter I for current. So the intensity of the current is equal to the charge Q divided by the time. So it's like a lifeguard looking at the charges in the circuit, counting the charges as they flow past the point. So the charge Q that flows past the point in a second in unit time, that's the intensity of the current. It's measured in amps. So 10 coulombs of charge per second, that's 10 amps in your circuit. But we want to think about where do these charges actually come from. And so what we'll consider is a giant cube of conducting metal like copper. Let's say I have a giant cube of copper. That's a meter on each side. I've got a cubic meter of copper here, a giant cube of copper. I don't need all that copper to make my wire. I need to just, take a little tiny piece of it, right, and draw it out into a wire. But I know something about a cubic meter of copper. So there's this idea called number density. The number density tells us the number of free electrons, or what are called conduction electrons, in unit volume of material. So this is why we sort of define number density based on a cubic meter of substance. And you can look up in a table the number densities for different metals, right? And it's really a sort of a chemistry idea. How strongly do the nucleons hold on to the electrons in something like a metal where you have metallic bonding or electron pooling? So the electrons aren't too tightly held to the nucleus. They're free to conduct, right? And so for an element like copper that has 29 electrons surrounding the nucleus of 29 protons, probably one of those 29 electrons is a conduction, or we say a free electron. So conductors, like metals, have electrons that are readily available to conduct. Again, there's like this free electron that can easily conduct. And you could look up what the number density is for copper. Somebody could do that right now. Actually, we could sort of quantify this, but it's like, something times 10 to it's a pretty big number, okay? Because we're talking about a whole cubic meter. So we need a way to sort of cancel out the cubic meter, right? Because this is telling us the number per cubic meter. But in my wire, I'm going to have a cubic meter. So let's say I take this little piece of my cubic meter of copper, right? I got this giant, maybe use orange color for that. A giant cube of copper here. I think we have at least one person out in the class that's looking up the number density of copper as we speak. So we'll be able to report that in just a moment. But we want to sort of cancel out the per cubic meter. So the number density of copper is equal to a certain value that's going to be forthcoming in just a moment here. That value, but it's the number of electrons. So it's like this number of electrons per cubic meter, right? It's defined as per cubic meter. So within my equation here, I want to get rid of that unit volume. Okay. I take my little piece of copper out of my cube. I draw it into a wire. Copper is ductile, so it can be drawn into wires. And I only have a small piece of this cubic meter. But in the whole cubic meter of copper, how many conduction electrons were there? 8.96 times 10 to the, I think you might have looked up just the density of copper. Oh, wait. You want the number density of copper. And that's a really good example of how we can sort of confuse two things that sound almost the same, right? So copper is like that many grams per centimeter, mass per volume, right? If you had a certain volume, that would be how much stuff is in it, how many kilograms or grams of mass. The number density has something to do with the electrons that are available to conduct, okay? So you have to look it up like that, the number density of copper. It should be a pretty big number, I think, like 10 to the, 20, 30, something, 28, 10 to the 28 something. Anybody have it out there?
6.022 times 10 to the 23rd.
That's Avogadro's number. That would be a coincidence. That would be a tremendous coincidence if it were equal to Avogadro's number. So yeah, I think you found Avogadro's constant with that one. 6.02 by 10 to the 23 is the number of carbon atoms and 12 grams of carbon 12. And so like that's a really important number, Avogadro's constant, because it gets us to like molar mass and sort of if everything on the periodic table is relative to copper or carbon rather being 12. And knowing that there's that number of carbon atoms and 12 grams of carbon 12, it lets us sort of convert everything. So that's a really important number, but not the number density of copper. So we got to keep on searching for it here.
8.5 times 10 to the 28.
Yeah, that sounds more reasonable. 8.5 by 10 to the 28. So just make sure that you're looking up the right thing there. Did you find it there in whatever resource you're pouring through? Copper is such a typical example that I feel like, I have gold right here. 5.9 by 10 to the 28 for gold. There you go, copper. Did you say 8.5 by 10 to the 28? Yeah, that agrees with that. And I got silver here too, also 5.9 by 10 to the 28. So silver and gold, 5.9 by 10 to the 28. Copper, even more. 8.5 by 10 to the 28. There's a whole bunch of electrons if I've got a giant cube of copper. Think about if I took a meter stick, it's a yardstick, what's that doing in the physics lab? If I built a cube out of meter sticks like this, so there's my length, the width, there's my height. Just imagine how big of a cube this would be, like off the screen, okay? If I had that much copper, right, just fill out the sort of cube here, there'd be this number of free electrons available to conduct. But I've taken just a piece of the copper. So I've just got now a cylindrical sort of section of copper wire, and it's got an area, a circular area, and it's got a certain length that I've drawn the wire sort of out into. Remember, that volume can be thought of as the two-dimensional area multiplied by the third dimension, depth, height. In this case, it's a length of copper wire. So let's go ahead back to our original general definition of the intensity of the current as charge per time. And we'll say, where are these charges coming from? They're coming from my metal, my copper, which has number density. But this is telling me the number of electrons per cubic meter. So I need to cancel out this cubic meter by multiplying it by the volume, right? So this is number per cubic meter. When I multiply it by area times length, right? So this is meters squared of area times meters of length. That's how I get my volume measured in meters cubed. So when I multiply the number density, which is electrons per cubic meter, by the volume, meters cubed, I cancel out meters cubed, and I just have how many electrons are in this piece of wire, right? Not in my whole cubic meter, my unit volume, but my actual wire, okay? I know how many electrons are in here. Each one of those electrons, which is equal to this gives me the number of electrons in my wire, has charge E, elementary charge, right? So this is actually what sort of takes the number and makes them charged, right? Every electron has 1.6 by 10 to the negative 19 coulombs of charge. That's elementary charge, right? That same value that's on the chalkboard. And then per time. Now I could write this T underneath this N. I could write this T underneath this A. Or I could write it underneath this L or this E, really anywhere, doesn't matter. But I'm going to choose to put this T right here, underneath the L. And that is not arbitrary. I did that for an important reason that I want you to think about right now, considering the whole goal of this was to come up with an equation that includes velocity. The mean drift velocity. I've got electrons in this copper wire. And when I hook up some EMF, okay, some energy per charge, some voltage, I can exert a force on these charges. I can create an electric field in the wire. Okay, and we already know that electric fields are regions of space where charges experience forces. So I can push these electrons, okay? They're moving with velocity. That velocity is what? Distance, length, divided by time. So I substitute in for L over T what it's equal to, velocity. And that's how I get I equals N A, L over T is velocity, elementary charge here. So this is the derivation, I equals nAve, based on the number density, which is the electrons per unit volume, canceling out the unit volume part, and then giving them all charges. Then we can see that the velocity shows up in this equation right here. And oftentimes we'll make that the subject if we're solving for the mean drift velocity. So V would be equal to I over N. Sometimes you'll see this with a lowercase q here, which is like whatever the charge is. But if it's like electrons or protons and things that sort of give rise to the charges in the universe, then it's going to be elementary charge E. So you'll see sort of, a slightly different form of this equation sometimes like that with a Q. And that just means, again, whatever the charge is, that this number of things, okay, has charge, Q, and oftentimes it's elementary.